Okay, pre-calculus students, for your second lesson after Christmas break, we just got done doing graphing exponential functions. And I did not use a calculator a single time for the ones I showed you because we just need to have the idea of where it looks, a couple good points, and what does it look like as I approach infinity, what does it look like as I approach negative infinity, are pretty much the important features that I need you to understand. We're going to go into now graphing logs. So the generic version of a log was log base b of x equals to a. And so I'm looking over here at the first two examples. He has a log and he has a exponential. If you recall, they're very much related. He starts out letting us know that not only are they related, they're inverse of each other. In a sense, they're mathematical opposites. So if I do a very generic graph of log of x, it's going to look like this. Asymptotic vertically, going up, 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 and going up and over that way. And I can tell you right now that that ordered pair is 1, 0. And you might be thinking, why was I so smart? How do I know that? Well, because this is log base 10. And it is the inverse of 10 to the x, which is exponential growth. Exponential growth meant as it goes to the left forever and ever, it's asymptotic on the horizontal. Then as it cuts through, it goes through the point, wait for it, 0, 1, and then the function continues to climb. Now, those two pictures, if you superimpose them on one graph, you have the exponential growth, then you have the logarithmic growth. Logarithmic growth did this. And if I extend this exponential curve a little more, you can see that there's some symmetry here. And of course, I did a free graph, so you can't really see it. But if I was to make an invisible line as y equals to x, it basically cut that picture in half. I want you to realize that this kept going this way. This keeps going this way. You see how that red dotted line is the middle of it? And then it cut through here. And then you've got on this side of the dotted line going straight down. And on this side of the dotted line, it goes straight across. Asymptotic horizontally, asymptotic vertically. Inverse of each other. That's what an inverse does. If you graph a function and its inverse, it always graphs as a nice pretty picture cut by y equals x if you wanted to graph that line. Okay. What did he write? To graph a logarithmic, you can use the inverse exponential function, then invert the values. He means switch the values in the table. In other words, I had 1, 0, then I know 0, 1 had to be on the graph. that might be what his method will be doing. So I guess I'll try that way. If we're graphing log base 3 of x, the exponential function was base 3. In this case, that's his y value. So that would have been the exponent equals to x. So if you could say to yourself, well, let's see, if I was doing 3 to the y equals x, and that's just an exponential function, because 3 is the base, and you make a table of x's and y's. I don't think I'm going to do it this way very often, just do it one time. If y was a 0, then the x is 3 to the 0 is 1. So I know 1, 0 has to be a point. Well, I showed you that a minute ago. That would be definitely a point. Let's do, what if y was 2? 3 to the 2 is 9. So now I gotta go 9, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2. Oh, yeah, look at what I see. This graph that looks like that. What do you think is happening to the left? Let's see, let's try a number that, what if I put a 1? I put a 1 there, if y is a 1. 3 to the 1 is 3. 3, 1. That doesn't really help. 1, 2, 3, y1. Yeah, that's on the line. So I would have to have something like a fraction. Like, what if I use a half? 3 to the half means the square root of 3. Well, isn't that between 1 and 2? 1.7, approximately 1.7. So that meant, actually, is that right? 3, square root of 3. X is 1.7, so it makes it a little more complicated. I'm just going to go down and just finish graphing the function. Oh, I did the right one, square root of 3. Basically, what I said to you is that your log function will be asymptotic to the y-axis. It's going to go up and cross the x-axis, then it's going to go increase forever and ever, up and over, up and over, up and over. So the domain of a typical, this log, since there was no shifting left and right, what do I mean? I didn't go plus a number. I didn't add anything to the x. I didn't add or subtract to the x. I didn't put any negatives anywhere. There's your parent function. The domain cannot be 0, but it can be all the other x's forever. The range can go down forever, and up forever. So negative infinity to infinity. The x-intercept was at 1, 0. If you recall, on the other lesson, we were asking for the y-intercept. We don't have a y-intercept in a log unless we shift it. In this basic log, we do not have a y-intercept. There's a vertical asymptote at y equals to 0. it's increasing from 0 to infinity. This is never decreasing. As x approaches infinity, that means to the right forever, f of x is approaching infinity. As x approaches to the left forever, f of x is approaching, it's always going to be approaching 0. It's never going to approach past that 0. Okay, there's one that I'd want you to be able to do by hand without a calculator. But feel free to try it with a calculator and see if you can make your answers fit. Now this one, because the base is a half, I hope you remember that this meant an exponential was the base is a half to the y equals to x. That was an exponential decay. So what you're going to find out is that the exponential decay is going to be the opposite direction than the exponential growth was. In other words, this is going down forever. The exponential decay will give us a log that goes up forever. Let's see if we can make it work. Let's make a table again, which is not my favorite way of playing around. But let me plug in some x's, some y's I mean. Let me plug in y is 0. 1/2 to the 0 is 1. So there again, I have 1, 0. There's your x-intercept. May as well put that there. 0, 1. Then let me plug in a y value of 2. 1/2 squared is 1/4. Oh, it doesn't go up very high. I mean, it doesn't, the x is 1/4. 1/4 is about, you zoom in here, and I put in a 2 for the y, so it's up here. Oh, do you see what's happening? Do you believe me now? So I don't really have to do any more. I can do one more. I can try to see what happens. What if y is a 10? Well, unfortunately, it's going to put it back in the same place. It's going to put it 1/2 to the 10th is 1/2 to the 10th. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 1/1024. It's very small. Very small. It's going to be way up here. Up the so that's what's happening here. It just keeps getting closer and closer to the y-axis going up that way. So here's my rough graph. You want to go to a calculator and get you another point that might work nice and pretty? Feel free. Asymptotic to the y-axis. That's going to come out, it's going to continue out something like this. It's just the flip of this one here, if you think about it. So the domain, again, starts at 0, goes to infinity. The range is going to be all real numbers. Does it ever, does it asymptote? Yes. Y equals to 0 is still the asymptote. Increasing? No. It doesn't have any decrease. It's not increasing. It's decreasing. From left to right, it's going down to the left. So it's going to be from 0 to infinity. And behavior? as x approaches infinity, f of x approaches negative infinity, because it goes down. As x approaches negative infinity, f of x, well, it's always going to be approaching 0 again. It can never go to, actually, it's possible that the solution doesn't even, it is possible the solution says it doesn't have, and this doesn't really exist, because it can't go to, that might even apply for this one up here. But I don't know. I'll have to look at it. There's two basic graphs that I would want you to do without a calculator. Oh my goodness. Not the y was 0, it's x is 0. X is 0. I should change these. It wasn't going to 0. I'm sorry. X went to 0. X is going to 0, but y is going to negative infinity if I was to keep that answer. And this was going to positive infinity if I was to keep those answers. Unless you want to just get more perfect. Now, what happens as we do natural log? It's no different. It's absolutely no different than the log. Because remember what this means. This means base is e to the y equals to x. So again, if I make my table and I say, well, let my y equals to 0, I get 1 again. So who am I kidding? And e is a number greater than 1, so it's going to be the same picture that I did a minute ago. It's just going to be a different values that would be in the table. But I'm okay with you doing this and saying there's your natural log graph. I don't need perfection. Just need you to understand the concept. From 0 to infinity, all real numbers is your range. 1, 0 is my x-intercept. Y equals to 0 is still my... Oh, what am I doing on every one of those? Yeah, y equals... It was x equals to 0. Did anybody catch that on the other two problems? I feel ridiculous. That's what happens when you're working at 5 in the morning. Increasing. It's always increasing. It's always increasing. From 0 to... Oh, what did I do that for? 0 to infinity. Never decreasing. As x approaches infinity, f of x approaches infinity. As x approaches to the left, negative infinity. Well, again, it never can approach negative infinity. So even though I'm saying f of x only approaches 0, it is possible that the author doesn't even address that. It just says that you can't, it doesn't approach negative infinity. It can't approach negative infinity. So there is a good shot that he doesn't address that, because it really doesn't go to negative infinity. Do another graph. With a transformation. Now, the only thing difference is there's a +1. And so this logarithmic decay, why do I call it a logarithmic decay? Because it came from a decay exponential. It was a decaying exponential, which meant that the exponential would have been doing this. Okay? So what I'm going to do is actually flip this over. That was a decay. And we know what a decay did. A decay ended up doing on the exponential look like this. Went down like that. That's what it did. Almost looks the same, except it's not in the same graph. If you graph them separately, if you were to graph y equals x to the 1/3, you would see it differently than log of 1/3 of x. If you were to graph those two together, you would see symmetry on the y equals to x. But anyway, it's going to be shifted 1 up. So all that changes is that we pretend that this axis here, I just draw it up here. And I say, well, there's my new axis that I care about. So the only point that I'm going to address that changes is the 1, 0 actually became a 2, 0. Because in the normal, it would have been 1, 0. But since everything gets shifted up 1, it's up here. That's my, so now if he asks me for my x-intercept, it's going to be harder. And he does ask for it. And it is harder to do. We'll try it in a second, but the y-axis still is my asymptote. So I'm going to draw towards it. And now it's going to come down this way. So everything looks the same, except you can tell that the x-intercept point moved up. Every point moved up 1. So the domain is still the same. From 0 to infinity. The range is still all real numbers. Now the x-intercept is going to be harder to find. And I don't know how important it is to find it, but we will try to use some algebra here. Okay, so if I want to find out what happens when y is 0, that's this bad boy here. If y is 0, log 1/3, base 1/3 of x plus 1. Okay, let me try to solve this for x. That's what I want to find out. I want to know what x is when the y is 0. I want to know what happens when the y is 0. What is the x? That's what I'm looking for. So here goes. Subtract 1 from both sides. Log of 1/3 x. Log base 1/3 of x. To get rid of the log base 1/3, I will exponentiate both sides 1/3 to the power. 1/3 to this side. In other words, both sides are being raised up. So this 1/3 to the log of 1/3 basically cancels out, leaving x equals to 1/3 to the -1, which means, if you think about it, the 1 gets a -1, the 3 gets a -1. It causes them both to flip positions. So x is equal to 3. Because if 1 gets a -1 and the 3 gets a -1, what happens is the top has to go to the bottom has to go to the top, leaving a 3 to the 1 over a 1 to the 1. 3. So there it is. There's your 3, 0. Which, see, how accurate am I? 1, 2, 3. Not very accurate. So if I wanted to, and if I would have done that first, it's not a bad idea, I guess, if you want a better picture, but I want to erase. Oh, X, boom. There it goes. Okay. I want to fix this up just a tiny bit. Then I can easily just do from there to curve in there. There you go. Looks okay. Asymptote is still going to be the y-axis, not y is 0. Y-axis. X is 0. Increasing? Never. It's decreasing from 0 to infinity. As x approaches to the right forever, f of x is approaching negative infinity. As x approaches to the left forever, f of x only is approaching 0. F of x. Wait a minute, was I wrong on the other one? Hold on. As x, we're talking about y, I'm sorry. F of x approaches infinity. What did I write up here? As x, I'm so wrong on all of those. I am going to fix them all right now, right in front of you. I'm not talking about, I'm talking about what y approaches. Well, no, it's the same thing. It's the same thing. Does x ever approach negative infinity? No. I guess it's the same kind of idea. As x approaches to the left, f of x is going up. But again, I don't think he's going to let me do that because I can never really, I'm truly not going there. Let's do one more. Now this transformation is that I am subtracting 2 from the x, which means right 2. Ooh, and there's a negative in front, meaning it flips over the x-axis. So I'm going to do a cheater method with you right now. I'm going to draw the parent, y equals 2 log base 2 of x. That looks like this. It's just a log, no shifting at all. Goes through the 0, 1, or I'm sorry, 1 comma 0, and it goes up forever, and it comes down forever, asymptotic to the x-axis. This picture has to flip upside down, and it has to shift to the right too. So what I'm going to do is I'm going to take this dot, 1, 2, I move it here. I'm going to take this asymptote that's right next to it, and I'm going to move it to 1, 2. So here's my asymptote now. Also, what else can I say? I went to the right 2. I need to flip over the y-axis. So what I'm going to do is take this picture here, and I'm going to draw it one time. I'm going to draw this here. Here it goes. Here is the shifted to the right 2. But this picture has to flip upside down. So what will the new picture look like if that flips upside down? I'm using my imagination. Now this thing going down is going to be coming from up here. Oops, not drawing. Yeah, there it goes. I quit drawing again. Come here, and it's going to have to go like this. I think that's the black flipped upside down. The blue was the original parent. I shifted it with the black 2 to the right, and now I'm flipping it upside down, reversing the whole picture. Does that make sense? So check it with your calculator And I'm going to erase the stuff that doesn't really belong to that picture anymore. None of this really is part of the picture anymore. None of this is part of the picture. Check it with your calculator. We will still have to answer the basic questions, the domain. This time, the vertical asymptote changed from 0 to 2 because it shifted right, so it's 2 to infinity. The range is still all real numbers. The x-intercept, did I actually calculate that? I haven't, and it shifted. So let me go ahead and do that work here. The original function is y equals to negative log base 2 of x minus 2. And so we want the y to be 0. So 0 equals to negative log base 2 of x minus 2. And get rid of the negative. Both sides still gives you 0 equals log base 2 of x minus 2. Exponentiate both sides to get rid of the log base 2. This goes away. This becomes 1. 1 equals x minus 2. Add 2 to both sides. 3 equals to x. So it's 3 comma 0. It's a good skill to do. Asymptote now is the x equals to 2 because it moved over. Increasing is never. Decreasing is from 2 to infinity. It's constantly decreasing. And behavior, the only end behavior I'm going to say I have is as x approaches infinity, f of x approaches negative infinity. I won't even do the other one because it's not approaching negative infinity. Okay, I'm going to do one more because it uses 2 transformations also. And then I'm going to be done. I'll assign you the other problems. The transformations in this one is a shifting down of 2 and a shifting left of 5. Down 2, left 5. If you want to make your life easy, draw your parent first. Log base 4 of x. It's very simple. Log base 4 of x means it had to go through 0, 1, and it's just a normal log curve, goes up, 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 over, over, over like this. Something like that. Okay? But there's 2 shifts. There's a shift down, and there's a shift left. So think about it. This point right here has to go down how many? 2 and left 5. So watch this. Down 2, left 5. 1, 2, 3, 4, 5. It has to be over there. And the asymptote had to go left 5. 1, 2, 3, 4, 5. So here is your new asymptote. So that same picture, here goes. It's going to look the same, except it's going to go through this point down here now, and now it's going to go up. There it is. This is a good representation of the new graph. You can make a table. You can play with points. The only point that he's asking me for is my x-intercept right here. So I'll do the algebra. Original problem. Y equals to log base 4 x plus 5 minus 2. Make that the 0, like we did before. Log base 4 of x plus 5 minus 2. Add 2 to both sides. 2 equals to log base 4 of x plus 5. Exponentiate both sides. 4 to that power, 4 to that power. This cancels out. 4 times 4 is 16 equals to x plus 5. X must be 11. So the ordered pair would be 11, comma, let's see, is it going to be 11, comma 0? Doesn't look like it. It should be negative. Let me look. Oh, wait. 2, 4, 16. Hello, I'm ready. I'm done.
Huh?
I'm done.
Okay, I cook breakfast in the kitchen.
Oh, okay. Let me get up. Let me, is it really? Oh, my fingers are numb right now.